All right, so my name is Joshua Watt, and today I'm going to talk to you about the software bill of materials and supply chain using the Yocto project. So a little bit about myself. I have been working at Garmin since 2009, and we've been using Open Embedded in the Yocto project since about 2016. I am a member of the Open Embedded Technical Steering Committee, and there's email addresses, IRC handle, Twitter, if that's still actually a thing, and LinkedIn, where you can reach me. All right, so a brief outline of things I'm going to talk about is what is a software supply chain? Why do we care about it? How Open Embedded, the build flow that Open Embedded implements really augments or provides a good software supply chain, what a software bill of materials is, talk about reproducible builds, and finally the Buildtools tarballs. All right, so what is a software supply chain? So software supply chain is just like basically any other supply chain where sort of generically there are three steps that you take to make something from components. So you might provision some sort of component from somewhere in the software world. This would usually be downloading some source code or a binary or something. And then we modify or combine that. So that might be compiling the source code, building an image from things that we've provisioned from somewhere or whatever. And then we publish or distribute that thing that we made for something else to then provision or consume like this. And so this makes this software supply chain, obviously, where there's this chain of things, and this goes over and over and over and over again to finally build up the end thing that we are producing. Some of the things that make the software supply chain particularly difficult, as opposed to maybe physical supply chains, is that there are a lot of these cycles going on in when you build a piece of software. There might be tens or hundreds of thousands of software components that go into your final product, and all of them have these steps that could potentially be taken advantage of. And there are actually known attacks. These are just a few examples of things that can happen at each of these phases of the software supply chain for any given component in your system. And if any of these are compromised, then that could compromise your your entire product that you've produced. And so the software supply chain can be particularly susceptible to these kinds of attacks at any point throughout the supply chain of your product. And there's been a couple of high-profile attacks that have targeted weak supply chains, like the SolarWinds hack and other ones. If you haven't heard about that, it's a pretty interesting read. And some of these attacks have gone unnoticed for months because people didn't know that their supply chain had a problem. And so the primary thing that we want to know about our supply chain is we need to be able to know what it is so that we can protect it and see if something is amiss in the first place. So that's really why we care about supply chains. And regulatory agencies have started to take notice of these things happening. And so there was the United States Executive Order 14028 that sort of strongly encourages or requires, depending on how stiffly you read it, that these supply chains need to be documented so that we know for software components what's in them. And the EU has a similar Cyber Resiliency Act that I don't believe has passed yet, but it is getting close, I believe. So what are the things that we actually need to know about our software supply chain? Well, I mean, the end goal is really like what's in the binaries that we're shipping to our customers, right? Or are using internally ourselves or whatever. So we would like to know all the software that's actually in it. Where did we get that software from? Could we trust where we got that software from? What version is it? We'd also like to know if we're complying with all of the software licenses, like GPL licenses or other copyleft licenses, or are there licenses that might have other requirements for use. We'd really like to know if the software has been tampered with, either maliciously or unintentionally, so that we can, correct those types of things. We'd like to know if the software is vulnerable to exploits, so we're not exposing ourselves or our customers to unnecessary risk. And really, a lot of these questions can be answered by asking if it's possible to trace the final deliverables that we've produced all the way back to the original code that produced them. And so a lot of questions can be answered if we can just answer that. So I'm going to talk about the open embedded build flow and how it sort of implements its own internal software supply chain, and how we have extended that in order to make useful software supply chain information. So when most people use Open Embedded or Yocto project to build something, they start with some source code from like some Git repositories or some tarballs or something. They have some metadata, like the recipes that we use that say how to actually build that source code. And they have some policy information that they might need. This would be like your distro conf, your machine conf, things like this that says like how at a higher level we want to build these things and combine them together to make images or whatever. So you chuck all of this stuff into this magical tool called BitBake, and it spits out this thing that we call a target image. And then we take that target image and we put it onto our widget and profit, or whatever it is you're trying to do with it. And when we talk about a target image, that can actually be a whole bunch of different things. It's sort of a generic term for basically anything we can produce that's, sort of an end thing that you might use. So we've got the traditional target image up there at the top, which might be an image that you would flash onto like a Raspberry Pi SD card and boot it up and go about your way. We can also produce target images for a whole bunch of different things you might not otherwise think of. So microcontroller firmware, we can produce that. We can produce images that can boot on x86 PCs if you want to do that kind of thing. QEMU, which was mentioned earlier in some other talks. We can also produce OCI compliant container images. Then there's also the package feeds, which are a type of target image that we produce. So this lets you publish the packages that you've built to like a server or something, and then you can have your device that was flashed with an image go download the packages to do updates instead of reflashing the whole device if you want to do that. And then a lot of the internal tools that we build, like the SDK and the extensible SDK and the Buildtools tarballs, those are also what we would consider a target image. So I'm going to go over a very sort of simplified build flow to kind of show how things propagate through the system when you actually invoke that bitbake command. So start off with a couple of things here. On the far left, we have the host tools. So that's going to be the basic tools that are required in order to run bitbake and build sort of stuff for your host systems. This is going to be Python, which you need to run bitbake, your host GCC, which is the GCC that you need in order to compile software to run on the PC on which you're doing the build, and a few other things like SED and BC, and I think a few other things like that. It's quite a small set of things you need. It's not too much. And then we have some source code and recipe metadata in blue, and those are what we call native tools. And those are really designed to build tools to, again, run on your host PC. And then you've got in orange, you've got the target source code and recipe metadata, and these are going to end up building stuff to run on whatever you're targeting to build. So that'd be your Raspberry Pi 4 or your SDK or whatever it is. And then we've got additional recipe metadata in yellow there that describes how to build images. So the way this works is we take those host tools and we process the recipe metadata, and we build what we call the native tools and the cross compiler. And again, these are tools that are designed to run on your host PC, but they are designed to help build stuff to run on your target. So an example of this would be obviously the GCC cross compiler and things like that, but also like the protobuffer compiler, for example. And so the thing to take note of here is that a lot of the tools that we are using in order to build stuff for your target, we're actually building internally ourselves, which allows us to keep things up to date and compatible a lot more easier, but it also really helps keep the number of host tool dependencies that you need in order to do builds to a minimum. So next step that we're going to take is we're going to take those native tools and cross compiler and things like that, and we're going to process more recipe metadata, this time for the target. And so we're going to produce a bunch of target packages. And then the final step that we take is we take those target packages and we process yet more metadata that says how to build an image. And we install those target packages into the image. And then you can go flash that on your device or whatever it is that you're going to do with it. So the way that BitBake keeps track of the dependencies between all of these things is using a very sophisticated method of hashing, where basically each step of the build process has a hash that includes all of the BitBake variables and tasks and stuff that are relevant for that task, but also the hashes for all of the upstream tasks that it depends on. So as an example, the do compile task depends on the do configure task. So the do configure task has a hash, and that hash will factor into the hash of the do compile task along with the actual text of the do compile task and all of the variables and stuff that go into it. And so because of this, if some hash changes, that's going to propagate through the entire system, and all of the downstream hashes from whatever changed will also change, and that's how BitBake actually knows to rebuild something when you change something. So just as an example, let's say we've got the protobuf compiler, the native protobuf compiler, and the source code for that changes. And so if that changes, what's going to happen is BitBake's going to see that that changed, which is going to tell it that it needs to rebuild the protobuf compiler, but that's also going to change all of the downstream hashes for everything that depended on the protobuf compiler. And so all of those hashes are going to change. And so that will rebuild the target packages, any target packages that depended on that, which in turn, since those hashes change, that means the target image hash, task hash changed, and so that's going to cause the target image to rebuild. And so this is a great mechanism for detecting when things need to be rebuilt. But this also means, from sort of a supply chain perspective, that we have a really strong mechanism that allows us to say like what went into the target image, and you can actually trace this back very strongly to the source code and the recipe metadata that went into the build in the first place. And so that is, at its core, that is a type of supply chain where we can trace this stuff back very accurately to these things. All right, so what is a software bill of materials? So software bill of materials is I really like this illustration where it's the nutrition information for your software. So just like on the food that you eat, there's a little label on it that says, what's in it, what are you putting into your body when you consume this thing. A software bill of materials is just like that, where it's sort of a standardized and concrete encoding that describes the more abstract software supply chain. And so there's a bunch of different formats for SBoMs that all might actually describe the same software supply chain, just with a different format. So there is SPDX, Cyclone DX, and there's another one that I can't think of off the top of my head. But those two are the kind of the main popular SBoM formats that describe that can be used to describe a software supply chain. So what actually is an SBoM? Well, it's a lot about describing what software is in your system, in your supply chain, and how that software is related. So they talk a lot about properties of software and then also relationships between software components in your software supply chain. And so this is a image that I borrowed from an NTIA document that kind of shows these Acme application that's being built, and they talk about how the different components that went into that are related to each other, and then what is known about these things and what's not known about these things and what versions and things like that. And I really like this diagram because I think it translates pretty easily and kind of describes our strategy for SBoMs in Open Embedded, which is if you take this and you just kind of put Carol's compression engine and Bob browser on there, that's basically at the end of the day how we're generating our SBoMs and kind of our concept for how this all works. And so because we have all of this recipe metadata, and a lot of this metadata is the stuff that we actually want to know and put into our SBoM. So our recipe metadata has versions and source code URLs, and it's got the licenses. And because we built everything, we know the runtime, the build time dependencies. You know, we had to know them in order to build the software in the first place. We know the runtime dependencies, and those more or less have to be correct in order for the software to actually run. You know, we know what CVEs we patched. We track that pretty carefully. You know, we know all the source files that went into this thing, and we know the files that we produced from actually doing the build, because that's all described in our recipe metadata. And importantly, like all of the information is authoritative. Like we have kind of taken the policy that we're not going to guess on things. We're going to provide the information that we know about from our recipe metadata, and kind of leave things that we're not sure about to someone else. This is how you create SPDX SBoMs in JSON format. I'm not going to cover this because Michael did his talk earlier about all this. But basically, when you do that, what happens is there's an extra step that occurs when you run tasks, and it generates these SPDX documents like Michael described, and they get put into that final archive at the end. So it just kind of adds this extra task that occurs throughout the supply chain, or sorry, throughout the build to produce the SBoM to describe the supply chain. As I kind of alluded to earlier, like what is the Yocto project's role in the software supply chain? Like what is the role and what we generate in the supply chain? So as I said, we really want to describe what we know about the build, you know, authoritatively. And then also not to try to guess and sort of, we're going to stay silent on things that we don't know. And it's not necessarily intended to be a 100% comprehensive supply chain, but it is a very important piece of the picture of an entire supply chain, and may be sufficient for what you're looking for your software SBoM needs, right? You may not need anything other than what we generate, but there certainly is a lot more information. So, for example, you may still need SBoMs from upstream projects in order to complete your software supply chain, or you may want to pull in tools that do post-mortem scanning of deliverables and things like that, which we aren't likely to add support for because it's sort of out of scope of the project. But you know, we are providing a important view of your software supply chain that is very difficult to get through other means. So some of the SPDX features that we are supporting. Currently, we have like declared licenses, the homepage URLs, the downloads URLs, CVEs fixed, the summaries and descriptions. A lot of these are, again, just straight from the metadata, so it's fairly straightforward what all of these sort of are. We can generate the list of all the source files that came from the upstream source code with their checksums. We do scan the upstream source code files for their SPDX license identifiers. We can produce all the packages and the checksums of the package files, and also the build time and runtime dependencies. And as Michael alluded to, we can generate those source code archives for analysis by other tools, like if you wanted to do busology. And a lot of this is pretty automatic. Basically, anything we can build for, we can generate some level of meaningful SPDX. So all of the on-target, like C, C++, Fortran, sort of standard compiler tools, we definitely can generate really good SPDX for that. And even all then the native tools and stuff like that, because again, they're just like any other recipe. So we can generate really good SPDX for all of that stuff. The Linux kernel we can generate SPDX for. We are one of, last I checked at least, we're one of the few products that can actually generate, or one of the few projects that can actually generate meaningful SPDX for the Linux kernel, which is pretty cool. And again, we can generate, the target images are just recipes, so they also get SPDX generated for them. The SDKs get SPDX. If you build a container image, you'll get the SPDX for that, VM images. I have Rest and Go under construction, sort of they need a little bit more work to handle the cargo crates and the Go, is it modules? I forget the exact term for the equivalent in Go. So like the base program or whatever that you're building in Rest or Go has meaningful SPDX, but it doesn't extend into crates and stuff that it pulls down. So there's a little bit of a spot there that could use some help if you're interested in Rust or Go and SPDX. I would encourage you to help out with that. So as I talked about, relationships between all the different things is very important in SPDX, and we generate a lot of relationships to sort of tie things together. And so this is, if you were to sort of graph it out, these are basically the relationships that we generate. And one interesting thing I would point out is that it's fairly straightforward when we produce a binary package that gets installed into a target image to say that that package was generated from the recipe that produced it, right? Which allows you then to trace that package back to the source code of that produced it, because all that source code is described by the recipe itself. But something else that's very powerful that we can do is we can actually trace binary packages back to other source code dependencies in other recipes based on the debug source. So the classic way that this happens is with static libraries. So a lot of times if you compile a static library into your application, it's very difficult to know that that's even happened post-mortem, but also then to figure out where that library came from. And so we can actually generate the link and describe that using this generated from relationship in SPDX based on the debug source. So when we look at the debug source for a program and we see, or a library, and we see that it has references to source code files from another recipe, then we know that it's used a static library or something like that to link those in. And so we'll generate that relationship that describes that, which is really powerful. It makes it a lot easier to keep track of static libraries and things. Or even if you just pull in the source code from another recipe or something and compile that into your application, that'd be the other way to do that. That would happen. Yeah, so I'm not going to detail all of these relationships because there's a lot of them, but you can feel free to peruse this slide later if you're interested. There's a lot of things that we would like to do in the future to make a lot of this stuff even more useful. We would like to improve the relationships, and we are talking with upstream SPDX about that. And we would like the ability to pull in upstream SBoMs if they provide them. So for example, if they have reuse in their repository or something like that. It'd be nice if there was an easy way to say, oh yeah, let's just pull in the SBoM that came from the upstream, and then we can link it into our SBoM with relationships and things like that. There's a ton more SPDX fields we would like to add about like how we built things and things like that with like the C flags and stuff like that, which I'll get to more later. All right, so we will now talk about reproducible builds, which is a pretty critical part of a supply chain. All right, so why do we want reproducible builds? I think probably one of the biggest reasons that we want reproducible builds is because it gives us more trust and helps us resist attacks and things like that in the binaries that we produce. Because if we build it twice or on different hosts or something like that, we can compare them and say, oh, what's different about this one than this one? It allows us to have more trust in our compiler. There's a good paper called Diverse Double Compilation about that, but it does require reproducible builds in order to work. Also, for quality assurance purposes, we want to know that the binary that we're shipping to our customers was at least really close to, but ideally identical to the binary that we tested before we released it. And so we'd like it so that every time we build something, we get the same thing every time. It also means smaller binary differences if you're doing delta updates for like software updates and things like that, and also increased development speed because it means that if nothing's changed, you'll get the same binary output. You might not need to rebuild as often. So if you're trying to sell reproducible builds to someone, the reproduciblebuilds.org website has this buy-in page that's really good for that. From like a build system perspective, we really want reproducible builds because we want to say that these task hashes that we're calculating actually correspond to a given binary that we're producing from that task. And the only way that really works is if the binary builds are reproducible. If you get two different binaries from the same hash, that means it's not reproducible, but it also means that our hashes aren't maybe as close to reality as we'd like them to be. And so just from that build system perspective, we really like reproducible builds for that reason too. So you can enable reproducible builds if you're using Yocto 4.0 or later. They're actually on by default. You don't have to do anything. They're just there. Prior to that, you can add this inherit line to your local conf, and that will enable reproducible builds. So what this actually does is it sets up some variables and some well-known variables and information and things like that, and does a few things to make sure that recipes can build reproducibly. It's still the responsibility of the upstream project to correctly consume that data. A lot of them do. It's usually not terribly difficult, but we have definitely had to submit a lot of upstream patches to fix things where they weren't correctly building reproducibly or things like that. Oh yeah, someone in the chat just pointed out that it's reproducible build without the .bb class. Sorry about that. Yeah, my bad. Yeah, so for OE core, we do a ton of reproducibility testing on the Yocto Auto Builder to make sure that all the recipes, at least in OE core, are building reproducibly. So this is, last I checked, about 11,000 target packages that we're testing. We aren't currently testing the native packages, although we would like to do that someday. And we're testing these across 3 different package formats. So that's IPK, Debian, and RPM, and we're building them across multiple build hosts, which means even if you do a build on Fedora and then do a different build on Ubuntu, you should get the exact same output, which is pretty awesome. So it means that we're not leaking some weird thing about the host into our builds. And it automatically generates Diffoscope HTML output for the packages that aren't reproducible. And Diffoscope's an awesome tool if you've never used it before. It's the diff, it will diff anything tool. It's pretty cool. But even though we're covering OE core pretty well, ultimately the only way to test that your specific configuration is reproducible with all of your layers and all of your configuration and all of that is to test it yourself. It's just not possible for the upstream project to test every single variation of every single package to make sure they build reproducibly. So if you really care about this, you do need to run these tests yourself. But we've tried to make this really easy. So you can put this 3-line Python file into one of your layers, and then run this OE self-test command, and that will test that your my image is reproducible. It does take a long time to do this because it has to do 2 almost full builds. I think it does exactly at least 1 full build of everything. And then I think it allows the second one to come from SState, or you might be able to control that. And then it will give you the report just like on the Yocto Auto Builder. It's the Yocto Auto Builder is doing the exact same thing as this. It's just got a different test. It tests a different thing. So we've decided that we've made this very easy so that you can test it yourself. Okay, I'm going to talk really quick. How much time do I got left? All right, I'm going to talk really quick about Buildtools tarballs. So this gives you your SBoMs and supply chain all the way down. So specifically, we're going to talk about this Buildtools tarball thing that we mentioned earlier. So what Buildtools tarball is designed to do is it's designed to replace your host tools. And since this is something that is actually built, by BitBake itself, what this means is all of the things that we've been talking about that are great for your supply chain can now apply to the host tools themselves, whereas before it might have been a little more difficult to make that connection based on where your host tools came from. So what this kind of means is if you really want to get super serious about your supply chain, you can build this Buildtools tarball, for example, on like an air-gapped host. You could distribute that to all of your people doing your builds, and then they can do their Yocto builds using that Buildtools tarball, and you'd be able to trace every image produced with that all the way back to that air-gapped Buildtools build that you did. So that could be extremely powerful if you need a deep and comprehensive supply chain back to some known trusted source. As we mentioned in the previous other presentation, SPDX 3 is coming out. So this is where we'd like to go with SPDX in the project. So we did the SPDX 2 support, and it went really well. I think we got some good output, and I think it's a good demonstration of like being able to have a supply chain that is comprehensive. But there is a sizable tooling gap, as has been mentioned. So there's not very many standard SPDX tools that can consume both our volume of output and the sheer number of documents that we output. And we kind of had to output the documents that way just because of the way that our build system works, basically. And kind of along with that, the spec isn't quite flexible enough to handle our complex document structure because it's really hard to merge documents in SPDX 2. And so because of that, that's why we came up with that tarball, where we just kind of put all the documents into a tarball, and you kind of just need to parse them all together, which again, the tooling doesn't support particularly well. And then there's not a lot that, there's a couple of things that I mentioned earlier that we can't really express. So like how we compiled things, like where things were built and things like that, and more precise CVE fix information and stuff like that. However, as I also mentioned, SPDX 3 is being worked on. I think they want a working draft in a few months' time, so that'll be great. And we've been directly involved in several of the working groups early to steer the direction and ensure that a lot of these things that we've been having trouble with the 2.2 get resolved for 3.0. And then ideally, I think what would be awesome is if we provided early working examples for the tool writers to test against, so that if we can produce early SPDX 3.0 output, that can be one of the examples that people use to write their tools against, and then we'll know that the tools can handle our output.